Hello, everybody. Today, lesson 2.6, related rates. We're tying into as things are changing, but as rates. So, as, say, area is changing at a certain time, say you're filling a pool, or as the volume is going to change, I guess that'd be more if you're filling a pool, but it's as those things are changing over time, that's what we're looking at for rates. Now, I'm going to skip the kickoff for this one. You can tell me later on if you'd rather have the kickoff, rather not, whatever you want to do there. But we're going to skip it on this one, and we're going to jump right into rates. So when we're dealing with rates, really it's going to be the same thing that we were just doing there, where we're going to use implicit differentiation to do this. However, everything is going to be in terms of time t. So if it's not a t, it's going to have a dx dt, a dy dt, whatever variable we're going to be involved with. So suppose x and y are differential functions of t and are related by the equation y equals x squared plus 3. Find dy dt when x is 1, given that dx dt is 2 when x is 1. So first thing we're going to do is we're going to find the derivative. So derivative of y would go to 1, but because it was a y, it's going to get a dy over dt equals x squared would go to 2x, but again, it was an x, so dx over dt. And derivative of 3 would go to 0, so it'd be gone. So this is going to be our derivative. So now it says, okay, find dy dt, so we're going to find what this equals when x is 1. So dy over dt equals 2 times 1 in for the x. It also says dx dt is going to be 2 when x is 1. So we can replace this dx dt with a 2, and we end up with 4. Now, for this one, it wasn't a specific rate, so we don't have a label, but typically they're going to have a label that we would go with that. So it's kind of how this is going to flow. So when you're doing this, you kind of want to separate a few things out, or at least identify a few things. And that's what I'm kind of setting up here with our equation, our given rate, and what we're trying to find. But for this one here, we have a pebble that's being dropped into a calm pond, causing this should be a ripple. Oh, causing in the form of a concentric circle, a ripple. Yeah, that's what I was getting at. The radius of our outer ripple is increasing at a constant rate of 1 foot per second when the radius is 4 feet, at which rate is the total area A of the disturbed water changing. So we're going to need a couple things here. First off, our equation. We're looking for at what rate is the area changing. So our area equation of a circle is A equals pi r squared. So area of a circle, have that equation for a while. What we need to look for then is, well, now what's our given rate? Well, it said we're changing at a rate of 1 foot per second. So that's how our rate is changing. So our dr over dt. So our change in rate over the change in time, given rate, is 1 foot per second. So lastly, what are we looking for? Well, we're looking for the change in area. So we're looking for dA over dt. Okay. So first thing always, find the derivative. We're finding the derivative of our equation. So derivative of A, well, it's not a t, so it's going to go to dA over dt. Pi is a number, so it's a constant. It's just a multiple that goes along with it, so we're actually just going to leave the pi alone. But r is going to go to 2r dr over dt. So derivative of A would go to 1, but because it was an A, it needs a dA dt. pi is a constant number, so it just moves down. R would go to r squared would go to 2r, and then because it was an r, it needs a dr dt. So now we can start filling stuff in. Well, we know dr dt is 1, so you can put that in there. We also know that our radius here is going to be 4 feet. So that is what r is. R is going to equal 4. So when we put this in, dA over dt is going to equal pi times 2 times our r of 4 times our drtt of 1. 2 times 4 would be 8, times 1 would be 8, so we're going to leave this as dA over dt equaling 8 pi. And we're doing area, so that would be feet squared per second. So, again, as you're going through these, if something's not quite making sense, again, send me a note, whether it's a pan or a message on Google Classroom. I will try to address these as best I can. You can always pause or go back through and rewrite stuff or rewatch stuff, and we'll get this. So here are some guidelines for kind of solving these related rate problems. Number one is you want to go through and identify all given quantities and quantities to be determined. So what are we given? What do we have to find? Always your first step, and that's with any word problem. Always find what are you given, what are you having to find. Now, sometimes it'll help to make that sketch and label it out. How is this going to look? Because sometimes a visual can help you kind of figure out what you got to do. Next, you need to write an equation involving a variable whose rate of change are either going to be given or to be determined. So that's where we went through that last one. We knew we had to find the change in area. We're dealing with circles, so our equation is going to be the area equation of a circle. Then we're going to use that chain rule and implicitly differentiate both sides of the equation to respect to time t. So whatever the variable is, if it's an x, you're going to get a dx dt with that chain rule. Because again, we don't know what each variable is, but it's not in the variable that we're doing the derivative of, so we have to assume that it can be differentiable. We can find that derivative of it at some point in time. So that's where we use the chain rule. Everything's going to get a dx dt, a dy dt, dr dt like the last one, and so on. Once we get that, then we're going to, so after we take that derivative, then we're going to take that result and put in those values that we know and be able to find out what it is and solve for that rate of change. So, air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when the balloon is 2 feet. So, given rate. Well, we were given that it's going at 4.5 cubic feet, so feet cubed per minute. Well, what is? Well, that's the rate in which air is being blown in, so that would be your change in volume. So we're going to call that dV over dt. Well, what are we having to find? Well, we're having to find the rate of change of the radius. So we're trying to find dr over dt when we're solving this. Now, at what point? Well, when our radius is 2 feet. So r is going to equal 2. And lastly, our equation. Volume of a sphere. Now, normally I would say I have this nice little poster over here on the wall by my desk. Look at that. That'll tell you the equation. You guys can't see that. So the equation of this sphere would be 4/3 pi r cubed. So volume of a sphere is 4/3 pi r cubed. So from there, we're going to do the derivative. So derivative of v would go to 1, but because it was a v, we need a dv dt. 4/3 pi, again, those are numbers. The numbers we don't do a derivative of if it's multiplied by our variable like this. So 4/3 pi. Derivative of r would go to 3r squared. And again, because it was an r, we need a dr over dt. Now, what's going to be different about this one is we're not trying to find what dv dt is. We're trying to find dr over dt. So we have to solve for dr dt before we can plug stuff in. Well, all this stuff is going to have to move over. But before we do that, let's simplify a little bit. We have a 3 on the bottom. We have a 3 up top here. Those 3's can cancel out. So we really just have 4 pi r squared. That's going to have to divide to this other side. So our dr over dt is really going to be 1 over our 4 pi r squared dv over dt. Now we're to the point where we can plug stuff in. Well, again, we know our rate that's changing, our dv dt is 4.5. So this here is going to be replaced with a 4.5. This other side, the 4 and the pi will still be there. However, our r is going to be 2, so 2 squared. 4, well, let's do this. 2 squared would be 4 times 4. This is really going to be 1 over 16 pi. And the 4.5 can really be on top. So if we divide that out, you're going to end up with 0.09. And this is our radius, so feet per second. Or not second, minute. Per minute, sorry. So, go through, find that rate, which it'll say it's changing at a rate of, so it'll kind of give you that rate. Well, what are we trying to find? Well, we're trying to find the rate of change of the radius. So, rate of change tells you dr dt, since r is radius. Always in terms of time, with our t on the bottom. It also says, hey, when the radius is 2 feet, so that's our r. Set up your equation, do the derivative, and then solve it for what you need to solve. In this case, we did the dr dt, not the dv, so we had to manipulate our equation a little bit to make it so that we had our dr dt out on one side. Then plug in your values and solve it out. Alright, so an airplane is flying 6 miles high on a flight path that will take it directly over a radar tracking station. If s, the direct distance to the tower, is decreasing at a rate of 400 miles per hour, when s is 10 miles, what is the speed of the plane? So this one here, a little bit harder to figure out what's going on, so let's draw a picture. So if we have our plane that's flying over here. This plane's flying. Over here we have our radar tracking station. Yeah. What really are we dealing with here? Well, we want to know what's the speed of our plane. So we want to know how fast is this plane going this way. If we know that it's 6 miles in the air, if this is our level ground, and we know that s is the distance to the tower, so s is this down here. So the direct distance to the tower would be from the plane to the tower. Well, what does that look like? It's a right triangle. So direct distance Actually, our S should be up here if that's the direct distance. So, start with your given rate. Given rate, it says, is it's decreasing at a rate of 400 miles per hour. So, that change in direct distance, so ds over dt, is the 400 miles per hour. We're also given that s is going to be 10. And we also know we're 6 miles high, so our h is going to be 6. We're going to make that our h. So, what are we having to find? Well, we're trying to find the speed of the plane, which speed is how fast is this side changing down here. So let's just call this x for now. We're trying to find dx over dt because x is going to be our position. So how much are we moving laterally? Equation we're going to need. Well, we're going to use this triangle to do that. So we're going to use Pythagorean theorem. So x squared plus y squared equals, in this case, our s squared. So instead of h, let's make this a y. So, well, if we already know what y is, we know y is 6, we can plug that in. So really we're having x squared plus 6 squared equals s, and this s should be squared. So we could go through and solve that out. So that this here is really 36. So when we do the derivative of it, x here is going to go to 2x dx over dt. 36 is going to disappear. Derivative of s would be ds over dt with a 2s in front. So we're trying to find dx dt. So let's solve for dx dt. We're going to divide by 2x. So dx over dt would equal, well, our 2's would cancel, s over x ds dt. So we know our s. Our s is going to be 10, but what is x? Well, right now we have 6. Let me draw this out again. We know this is 6. At this moment in which we're changing this here, our s is going to be 10. So we can put 10 here, and we can find what x is by, again, doing that actual Pythagorean theorem. So 6 squared plus x squared equals 10 squared. So 36 plus x squared equals 100. And if we subtract the 36 over, x squared would equal 64. And when you square root that, x is going to equal 8. Now, do we need to worry about the plus or minus here since we square rooted? In this case, no, because we're dealing with the distance. We can't have a negative distance. All distances are going to be positive. So if x is 8, then we can plug that stuff into here and be able to find this out. ds dt we said was 400. So we're going to have 400 here. S we know is 10. So we're going to have 10 over our x, which we just found was 8. And that's going to equal our dx over dt. Now, if we solve this out, how many 8s go into 40? Well, 5 of them. So there would be 50 that go into 400. 50 times 100, or 50 times 10. Getting ahead of myself. 50 times 10 then would give us 500 miles per hour for our speed. So Just to recap, again, flying at 400 miles per hour is how much it's changing. Well, that's this S, that's this slope. When we're a certain distance away, so our changing rate, ds over dt, 400, when S is 10. We also know our height is 6 miles, so that's our y. So we set up our equation using Pythagorean theorem. Since this is a right triangle, we can go through, we can solve that out. Now, to find that other variable, then we set up that right triangle again at that exact moment. This would be 6, this would be 10. We could calculate what x is, which was 8. So we could put that in and then solve it out. All right, so find the rate of change in the angle of elevation of the camera 2,000 feet away from a rocket at 10 seconds after liftoff, which is s feet high. S equals 5,000 feet high at 10 seconds, so we're going to keep that in mind here in a second. It has a velocity of 100 t, gaining 100 feet per second of speed. So, if we draw this out first, so here is our guy with our camera. Now over here is going to be the rocket. I know that kind of looks like a goldfish, but it's going to be shooting up into the air. So as this guy is over here with the camera, as it's going up in the air, we're wanting to find how fast is this angle, which I'm going to call theta here, going to be changing. So what we know is we are 2,000 feet away. So this is going to be 2,000 feet. We also know at 10 seconds, this side here is going to be 10,000 feet because S is going to be the height of the rocket. So, again, dealing with the triangle here, well, what do we know? We have an opposite side, we have an adjacent side, and we're looking for the angle. So we're going to end up using a trig function tangent here to do this out. So, tangent of our theta is going to be equal to our opposite, which at this moment for this rate is 10,000, but this is going to be changing. So we're going to leave that as an S. And then our other side, which is adjacent, will be the 2,000. And that's actually going to be the equation we're going to use. So, derivative of this, well, derivative of tangent is actually secant squared of theta. The other side, the only variable we have is S, which is going to go to a 1. So 1 over our 2,000. But because that was an S, we need a ds over dt. Now, the one thing I forgot, this theta, though, is another variable. It's not time. So we really need a d theta over dt here. Now, we want to find the rate of change in elevation. So we're looking for this d theta dt is what we're actually doing, because we're looking for how is this changing this angle? How is that opening up? So we need to solve for this now before we can start figuring anything else out. So d theta over dt, we would divide by the secant squared of theta. Divide this by the secant squared of theta. So actually, why don't I put it on the backside of 1 over secant squared theta. So still dividing by it. That side cancels out. So d theta over dt would be equal to, well, 1 over secant squared. If you look in your book for the trig identities, 1 over secant squared is actually going to be cosine squared. Cosine and secant are reciprocal functions of each other. So we're actually going to have cosine squared theta over 2000 ds over dt. So again, 1 over secant, reciprocal identity with cosine. Because it's squared, it's going to be cosine squared. So from here we can start figuring up some stuff. Well, ds dt is, how is s changing? Well, it says it has a velocity of 100 t. So 100 feet per second is squared. That's your change in position. That's your velocity. So ds dt, we can sub out and put in 100 t to get it in terms of time. Now, the only thing that we need to find yet is, well, what is cosine squared of theta going to be? Because, again, we need numbers to figure out how is this changing by. So we're going to have to figure out what is cosine squared of theta. Well, if we come back over here to our triangle, if I redraw it here, we know that S is going to be 5,000 feet. Why I put 10,000, I don't know. This should be 5,000. Sorry if that caused confusion. I think I was going off 10 seconds, 5,000 put together. Sorry. So, we know this is going to be 5,000 over here. We know this is going to be 2,000. We don't know what our third side is when theta is our angle. However, we can calculate that again by doing Pythagorean theorem. So x would be 2,000 squared plus 5,000 squared for our y over our c squared. So, the only thing to get c by itself then is we would square root both sides. So for now we're going to leave these as they are and just have the square root of 2,000 plus 5,000 both squared as our c. So cosine, then when we rewrite this, is so ka toa, so sine opposite over hypotenuse, cosine adjacent over hypotenuse. So our adjacent is 2,000 over hypotenuse of this. So we're going to have d theta over dt equaling cosine would be, like I just said, so the 2,000 over our adjacent or hypotenuse side of this, square root of 2,000 squared plus 5,000 squared, whole thing squared. Well, we still have this 2,000 on the bottom that we can't get rid of, but we have our 100 t on top. Well, what is our t? Well, t is at 10 seconds. So we can put that in. And from here, if you multiply this all out, you're going to end up with 2 over 29. And if you don't believe me, let's put it in the calculator. So, I'm going to put parentheses, and I'm going to go into my fraction deal with the alpha y equals button. On top, we have 2,000. The bottom, we're going to have a square root, which is second x squared, of 2,000 squared plus 5,000 squared. And I'm going to get out of this and then close my parentheses, actually, and then raise it to the second power. That then is going to be times, and again, we're going to need a fraction, On top, we have our 100 times 10. On the bottom, we're going to have our 2,000. When you do that, you get this decimal. And if we hit math, frac, there's our 2 over 29. So, so 2/29ths of a radian is how our angle is changing per second. So again, radians, if you think back to that, we have degrees to measure angles. Radians is another form of that. Think like British standard and metric, just two different ways to measure it. It's still the same sort of thing. Radians, though, in one circle is 2 pi, where degrees is 360 degrees in a circle. So just think that's how much of a radian we're changing by is 2/29ths. And so that would be our then. So we'll call this rads per second is what we're changing by. All right, so lastly, so an engine has a 7-inch connecting rod fastened to a crankshaft of radius 3 inches. The crankshaft rotates counterclockwise at a constant rate of 200 revolutions per minute. Find the velocity of a piston when theta equals 1/3. Now, I'm sure many of you are going, okay, what are all of those words meaning? Well, normally in class, this is where I can pull up a nice little video of showing how engine works. I could still do that if you want. I can find that. But for the most part, if we look at this being just a side view of an engine, if we cut through there. Up here we have our piston that moves up and down. So this is going up and down this way. Up here would be your spark plug and your valve and your other valve. So you have a valve that allows the air in and your gas in. Your other valve allows the exhaust back out once it sparks. Okay. But in this engine, we have our crankshaft that has a piece here. Now they're all timed based off of what the piston is, but that connects up with our rod so that as that's moving up and down, that's turning, which in this case is counterclockwise, so it's turning this way around. So as that goes up, this straightens and then pushes it and then pulls it back up and gets that circular motion going, even though this is a vertical motion. So piston, crankshaft, here's your connecting rod, connecting the piston to the crankshaft. So what we're really forming here is, if I come down like this, is we're going to be forming a right triangle with this. Well, not quite a right triangle, but it's forming a triangle. So our connecting rod is 7 inches. The crankshaft, so this width right here is going to be 3 inches. And it's rotating counterclockwise at 200 revolutions per minute. So that's our rate, is 200 revs per minute. All right, so now I gotta think a moment, because our theta, trying to think of where theta goes. Okay, so an engine has 7-inch connecting rod fastened to a crankshaft of radius 3 inches. Crankshaft rotates counterclockwise at a constant rate of 200 revolutions. Find velocity of the piston when theta is pi over 3. Okay, so give me one moment. I wish I could pause this, but I can't. But I'm going to get my book out here, and we're going to look in the book at the picture they give me to make sure we're putting theta in the right spot. So before I lead you astray, I'll look this up here quick. Okay, so here's the picture in the book. So our theta is going to be between the connecting rod and straight up to the piston. So this angle measure in here is going to be our theta. So, well, what are we finding? Well, we're finding the velocity of the piston. So velocity, we're going to use, we're going to call this just dx for now. X being the velocity, so dx over dt. So from here, this is going to be our x. So how fast is x changing? And we want to do that when theta is pi over 3. So you might be asking yourself, what sort of equation are we going to need here? We're actually going to use the law of cosines, which some of you, if you've taken physics, Dylan, you're going to be so excited you're actually going to use your law of cosines that you keep writing on the board. But that's what we're going to use here. So C equals, do you want to do C? So it's always opposite side here. So just think C is this crankshaft. What I remember is C equals our A squared plus B squared minus 2AB cosine of our angle. Well, now we're going to start filling stuff in. So if we're from the angle, C is always opposite side of that angle that goes on the outside. So that's our 7. So 7 squared, and C squared, sorry, equals our A squared. A in this case is going to be our connecting rod here. So 3 squared plus our other side, which is x squared. These here are interchangeable. You can have them in either spot, so it really doesn't matter which one's A, which one's B. But what does matter is we're going to have then a minus 2A, so 3 times B, which is x, cosine of our theta. Now, we don't know what theta is right now. We're just going to leave it for the moment until after we take the derivative of this, and then we can plug in what theta is. So this here would be 49. 3 squared would be 9. And this here would be 6. So when we do the derivative of this, derivative of 49 is going to disappear. And so this here will just be 0 equals 9 again will disappear. Derivative of x though will go to 2x dx over dt minus our 6x. Well, x is going to go to 1. So minus 6, but again a dx over dt. And then derivative of cosine is a sine. I take that back. We have to do product rule here because we have two functions times. So derivative of the 6, x would go to 6 dx dt cosine theta plus, I'm going to put this in parentheses, our 6x derivative of cosine would be a negative sine. Theta, and then we need a d theta over dt. All right, so from here, we can start simplifying. Well, what could we pull out of this here? Well, we're trying to solve for what? We're trying to find dx dt. So we're really going to distribute this negative in, and and that will cancel this one here. And anything that has a dx dt has to go to the one side, so we're going to subtract our 6x sine theta d theta over dt to the other side. So what that's going to do is it's going to leave everything that has a dx dt on this right side. So we would have negative 6x sine theta d theta over dt equaling 2x dx over dt minus, because that minus got distributed, 6. I'm going to move the cosine theta here first, and then the dx over dt. Now we have a common factor we can pull out front, dx dt. What would be left then is your 2x minus 6 cosine theta, which over here is equal to a negative 6x sine theta d theta over dt. So then we'll divide this to get our dx dt by itself, so 2x minus 6 cosine theta. And what we do to one side, we do the other side. So 2x minus 6 cosine theta. So at this point now, we can start substituting stuff in. If we put theta into this original here to find out what our x is and solve, our x is going to end up being 8. If you want, I can go through and show you how to do all that. If you do, leave me a message on Facebook, or not on Facebook, on Google Classroom, or send me a pan, and I can make that up and show you how that's going to work. But I feel like it's just going to confuse you more at this point. So just know that at this point, when theta is pi over 3, our x here is going to be 8. So this is our rate. This is how theta is changing by. So this is d theta over dt. So now when we plug stuff in here, dx over dt would equal, so negative 6, and our x is 8, sine of pi over 3 over 2 times 8 minus 6 cosine pi over 3, all times 200, which is the dx dt. So solve all that out. What you're going to end up with is negative 41.8, and this is inches per minute. And that's it. Now, went through this problem to kind of show you how this is. I feel like this one's complicated enough. I didn't actually give you one of the homework problems. I took that one out. So that's one you're not going to have to worry about. But again, when you go through this, if you need to watch the video again, if you have questions, you want to send me questions, pan me, Google Classroom, email, any of that works. Send me those, and I will try to explain the best I can. Other than that, good luck, and we'll talk to you guys later.